Okay, greetings everybody. I wanted to do the video earlier from today. Again, wasn't quite feeling well, and I don't know, something over the weekend. Try to shake it today, but feeling somewhat better now. And I wanted to do a better job at describing at least the basics of centripetal motion. If you understood it today, great. That's awesome. But I just feel like I wasn't giving you 100% because I wasn't feeling too well. So I'm going to start off with the demonstration video again, and then we'll go right to the main topic. Okay. Oh, here we go. And so again, this is the same demonstration earlier, circular motion demonstration with the sparkler. Whoops, let me stop that. And go back.
This is a great demonstration for showing that if something's moving in a circle and you remove the centripetal force, it'll move in a straight line. But if you're teaching circular motion, I've got another demonstration that's worth doing first. This is a really simple way to introduce some basic ideas about circular motion. The ball moves in a horizontal plane, which makes it easier to understand the forces involved than with, say, something moving in a vertical circle, because we can ignore gravity. When I do this with my students, I place an object about there and I ask them to tell me when I should lift the hoop so the ball knocks it down. Right, so as a physics teacher, I knew when to lift the hoop because I knew the ball would go off at a tangent. But that's not obvious to everyone, and this demonstration can really help to clear up misconceptions about things flying off radially when you remove a centripetal force. The ball goes from moving in a circle to moving in a straight line. And we know from Newton's first law that if something is moving in a straight line at a steady speed, the resultant force on it is zero. So what's going on when it's in the hoop? Well, the hoop exerts a contact force on the ball at right angles to its surface, and that force changes the velocity of the ball. The force is always directed towards the centre of the hoop, the centre of the circle. Take away that force and the ball obeys Newton's first law and carries on moving in a straight line. This is true of all objects moving at a steady speed in a circle. The instantaneous velocity is always at a tangent to the circle, and the force keeping it moving in a circle is at 90 degrees to this, that is, towards the centre of the circle. We describe the resultant force that makes something move in a circle as a centripetal force, and it's important to emphasise to students that this word simply tells us the direction of the force and nothing more. The force may come from a contact force, as in this example, or friction, or gravity, or tension in a string, or any combination of these forces, so it's really important to look carefully at any particular situation to identify the origin of the centripetal force. This is really just a more exciting version of the demonstration with the hoop and the ball. And it's not as dangerous as it looks. If you're going to do this in class, wear some goggles and a lab coat to protect your clothes from any stray sparks. Stand your students a couple of meters back in a plane that's parallel to the plane of rotation of the sparkler. You simply jam the sparkler into your drill, making sure it's secured tightly, bend it at 90 degrees, ignite it, and off you go.
Okay, so let's get back to our screen here. So just cutting right to the chase. What we're going to do today is show why there is something called a centripetal force that could be set up by friction, as you mentioned, friction, gravity, tension, any type of net force that could create an acceleration towards the center of the circle. We're going to show today why it points to the center of the circle and keep the object moving at a constant, what we call a tangential velocity around the circle throughout its whole path. So what I'm going to do is go from a linear description of motion to a circular description of motion, geometrically as well as diagrammatically and with definitions. So let me just label these two items here. So this will be, this particular force would be a centripetal force. And that force will be seeking the center, because centripetal means center seeking, which we'll see again. And VT is our tangential, or we can just say outside velocity, the velocity that's on the outside of the circle. There is an acceleration because the direction of the velocity vector changes. So as he comes around here, that VT is going to be there, and then there's going to be a centripetal force directed always perpendicular to the constant velocity. Magnitude doesn't change, but the direction does. Therefore, there's an acceleration. We're going to prove all that today. So first of all, we know, going back to first principles, that displacement is final position minus initial position. And then I can have a point here, and it's x final, x initial, like so. Well, then I translate this way, to my final position. It takes a certain amount of time to do so. And we know that the rate of change of position, or delta x over delta t, is velocity. So not only are we seeing a displacement, we're seeing a velocity at the same time, because it takes some time to change that position, and given by this equation here. The particle could be, moving at a constant rate. So this would be speed v at different moments in time. First second, second second, third second. It's going to be a constant velocity in the x direction, or even in the y direction, if we somehow eliminate the acceleration of gravity. But for the sake of argument, we can make a constant velocity in either situation. Now, we know that there's going to be an acceleration by the application of a force along the x-axis. So the velocity vector, I'm just going to draw it a little bit smaller and then enlarge it. So it's going to go from a very small value to ever increasing values. So this is my velocity, but I also know at the same time that there is a constant acceleration every second that's going to increase the velocity every second. So this object is going to be speeding up, since the acceleration vector and the velocity vector are in the same direction. So I'm going to label this as 1 and 2. And in this case, the first case, acceleration is equal to 0. So as a particle is moving at a constant speed along the x-axis to the right, there is no acceleration. There's no outside force that's going to change the velocity. The velocity is going to be constant every second. And in the second case, there's some outside force that increases the velocity, and that is what we know as an acceleration, because acceleration is going to be your change in velocity over change in time. So for this acceleration here, we have delta v over delta t. Okay, so that's a standard operating issue for stage number 1, step 1 here. That's just going to be constant velocity, along the horizontal axis. along a straight line. And even in step 2, even with the velocity changing, we're going to have a constant acceleration along the x-axis as well. But now, if we go from linear motion to rotational motion or uniform circular motion, things change just a bit as far as the direction of the acceleration when the velocity actually does change. In step 2, we see that the velocity is just changing in magnitude, but has the same direction. And that obviously produces an acceleration here, because we know by definition that acceleration is change in the magnitude and or direction of velocity. So this situation here in step 2, we're changing the magnitude, keeping the direction the same. But in circular motion, we're going to see that we're going to be changing the direction but keeping the magnitude the same. So brings me to the next point of now an object not moving in the x or y direction under the influence of an acceleration or not, to uniform circular motion, which is the topic of section 4.4 in your textbook. So section 4.5 is slightly different. So section 4.4. And so basically, uniform circular motion, what described earlier is just, we have the same particle as we see in pictures 1 and 2, but we have this particle moving around a circle at constant speed. We're going to say speed, and same thing as tangential velocity, but it's really a speed because we're just talking about the magnitude. But that just depends on how we're looking at it. If we're just looking at the magnitude itself as it's changing, we're just looking at a speed. But when we look at the whole thing, obviously it's just going to be a velocity because that speed is going to be changing direction. So for the sake of clear argument, I will just write this as constant velocity. But that's the thing in physics, a lot of times context, we understand the context, even though the word is different, but it's best to be as accurate as possible whenever you can. So a particle moving around a circle at constant velocity. But the direction is changing, so it has an acceleration, and we know the direction is changing because like it goes around the circle, it's going to be pointing differently at every point along the circle. So the direction of that pointing velocity, that linear velocity, which we're going to prove again in the next step here, the direction is changing, but the magnitude stays constant. So it has an acceleration because the direction of the velocity changes. So basically, uniform circular motion, it's constant circular motion. Constant, we say, because there's a constant velocity. The value of the velocity doesn't change, but the direction does. Therefore, there's an acceleration that we're going to prove points towards the center of that circle. Okay, so let's move on to our next part. So if we were just taking a look at a displacement, so an object is moving along, it's moving along say delta x in a certain amount of time. It has a particular velocity because we know that velocity is the rate of change of position, the rate of change of which is displacement over time. We've also seen that if an object moves along a curved path, that's going to be the distance that it travels, or displacement of the object, that the velocity at any moment in time is what we call the instantaneous velocity. And let's say that if I have my particle here along this path as it moves, say up and over from left to right, at this moment, there's going to be a velocity that's tangent to that path. So that's why we give this particular quantity, we call it tangential velocity in a circle, because that velocity is going to be tangent to the outside of the circle. And we say that is VT, or tangential velocity. So at that moment, the velocity looks like that with respect to the path. At another moment, let's say the particle is here, the velocity is going to be roughly pointing in that direction, and here. And so you get the picture, this different moments of the particle as it moves around a circle. So put them all together, we can get an appreciation that the velocity on the outside, which is going to be the slope at that point, that's what we call the tangential velocity at that particular moment, which is same thing as saying instantaneous velocity that is tangent to the outside of the circle. Simply put, it's the tangential velocity of the particle as it moves around the circle. So putting it all together, so we have the particle here, there's going to be a tangential velocity that points in that direction. Particle here, tangential there, and so on, roughly the same magnitude. So you may be asking yourself, why or how does this particle move around the circle and points in different directions? Well, it is under the influence or application of a centripetal force. There is a centripetal force that's causing this velocity, even though it has the same magnitude at every moment. That centripetal force is causing the velocity to change its direction around the circle. And so what we need to do first is prove that statement, that there is a centripetal force. And as there is a centripetal force, there's got to be a centripetal acceleration. So what we're going to do is prove geometrically that there is an acceleration towards the center of the circle. And then we're going to take that geometry and derive an equation for centripetal acceleration that we can use in problems and so forth. So this is what we have at the moment. At each of these moments, tangential velocity, this guy up at the top, and going around, just choosing arbitrary clockwise, you can be counterclockwise, it doesn't matter. So now let's extend definition a bit. So we've already seen this situation, say XY plane or the circle going around. And if we were going to go counterclockwise, this circle has a radius. So the particle on the outside of the circle has a distance r away from the center of the circle. It is going to be subtended by angle theta, and it's going to be covering a certain path that we call the arc length. That's going to be more important to the rotational kinematic stuff, but just to get an initial picture of what's going on there, we know that the arc length is given by radius times the angle theta. So given the picture up top, this guy here we can then say, let's take this particle and give it an arbitrary direction. Let's say it's going to go clockwise. Let's say that the particle at some initial time is here, and then some final time is right there. So that particle in both situations, it's the same circle, so it has the same distance at each time. But we're going to say Ri and Rf because those are two different times, just to keep the argument consistent. So this is final time, initial time, and of course at this moment it has a velocity initial, and over here it has a tangential velocity final. Let's just use that as our case. So as we can see, we'll see soon that there's going to be a central force here that's causing this velocity vector to change direction, even though the magnitude is the same. The reason why the magnitude is the same is because there's no outside force tangential to the object's path on the outside of the circle that's going to change its velocity tangentially. That's the subject of section 4.5. But right now, we're just going to say that all the force is directed towards the center, which we're about to prove. And that force sets up an acceleration. It's also going to be pointing to the center. So let's take a look at those velocities and use the definition of acceleration to show that this particular acceleration is central. So again, acceleration is change in velocity or change in time. And we've already stipulated that acceleration is a magnitude of a change in the magnitude or direction of the velocity. In this case, it's the velocity's direction is changing, but its value is constant. It's going to be 2 meters per second, 2 meters per second, all the way around, because there's no force out here that's going to change it from 2 to 4 to 6 or whatever. So now, just roughly drawing that picture again. Again, its scale is not too important here, but I'm trying to make this as accurate as I can. VI, and then let's see. VF. So this is sometime final, sometime initial. That is projected at these two different directional velocities. Okay, now we're changing the direction, and we know that acceleration is final minus initial, t final minus t initial. That's the equation format. So now let's represent that geometrically. So again, I have the circle. V final is here. Roughly V initial, or it's the opposite of this vector here. VI is going this way, then negative VI goes the opposite way. And vectorially, we have a delta V that, by my poorly drawn picture here, but roughly points to the center of the circle. And that's going to be the case for any two pairings of the initial and final velocities. So that's just delta V. How does that become acceleration? Well, we know it takes time to change your velocity. It takes time to change position. It takes time to change anything. So this delta V is going to be with respect to a change in time. So you can pretty much say that this delta V over delta T is going to be the acceleration towards the center. That's just the geometric look of it. So it stands to reason, is this acceleration to the center of the circle that we can denote as centripetal acceleration? Is that also delta V over delta T? Well, it is not, okay, because we have to do something else with the radial distance, the RI and the RF vectors. And the real reason why it's not delta V over delta T is because it's not moving in a straight line where the dependence is only one axis. This would be, let me just take that off. This acceleration here will be with respect to one direction, X, Y, Z, just a constant acceleration. The acceleration that we see here, delta V over delta T, is essentially that's what it's going to be, involves not only the velocity vectors, but it involves the distance away from the center of the circle. So we're going to make a relationship between our velocity vectors here and our radial vectors. They have similar relationships there. These two velocities are the same value. Okay, let's say that that's 2 and this is 2. They have the same magnitude as we go around the circle, just as these R vectors have the same value because it's the same radius. It's just we're looking at the radius, the same radius at different times. So that's why we call them RI and RF. So again, the particles here and there at some initial time and some final time. So now we're doing the same geometry or similar geometry to the radial vectors as we did to the velocity vectors. And what we have here is we're going to see delta R, which is final radial vector minus initial radial vector. So we're going to have RF pointing this way and try to put that in there a little bit better there. So RF and the negative of RI, which is going to be pointing something like this. And so this is negative RI. So basically, we're just doing the geometrical analog to this equation here. And the difference between the two would be delta R. So we have to treat both the velocity and the radial vectors for this particle because the particle is, both of those vectors are involved in the motion of the particle around the circle, as opposed to, okay, we have an x-axis or a y-axis and just, okay, delta V over delta T and we're done. So that's basically why we have to do that, because both of these quantities are involved in the motion of the particle. Well, as we do that for both the velocity vectors here and the radial vectors there, we can form a similar triangle relationship. We can state that delta V is to V as delta R is to R. And why is that? The angle between these two pairs in velocity and in the radius are the same. So that's how we can come up with our similar triangle logic. Something borrowed from geometry there, but again, just presenting it as such here. So V and R on the denominator. Well, that's the same thing as saying VI equals VF, which is just its outside velocity or the tangential velocity, much like the initial radius and the final radius is just nothing but the radius. So that's why this similar triangle relationship works, because delta V is to V as delta R is to R by similar geometry, just similar triangles. Now, having this relationship, we go back to our original equation for acceleration. Let's use this relationship here to get a new expression for velocity and see what we come up with for that acceleration that is directed towards the center. So using the relationship up top, we can solve for delta V, multiply both sides by V, then we'll have V divided by R and delta R over delta T. Well, this delta R as a radial vector is just another distance or displacement over time. So this is my radial displacement over time. So this is like another velocity in the radial direction. So this just becomes V divided by R times V. And that just basically becomes V squared over R. So the acceleration directed towards the center that we denote as A sub C is equal to V squared over R, where V here is generally denoted as the tangential velocity because, you know, that's what it is there. But sometimes we just leave out the T because we understand that that's the velocity on the outside of the circle. So AC is centripetal acceleration. VT is my tangential velocity, and R is the radius of the circle. So different from our standard definition of acceleration, which is delta V over delta T. Centripetal acceleration is A sub C equals VT squared over R, just V squared over R, where V is the velocity on the outside. Never, in this case, never changes magnitude, but always changes direction under the power of a centripetal acceleration caused by a centripetal force, which is just an easy add-on to this problem. So that's just where that equation comes from, centripetal acceleration V squared over R. So let's see here. Guess we can go over the same examples of earlier today. 1 second. All right, everybody. Okay, so I'm going to go back to the example, a couple of examples that we did today in class. Page 94, number 26. So as their booster rockets separate, space shuttle astronauts typically feel accelerations up to 3g. So again, this is 94, number 26, where g is 9.8. In their training, astronauts ride in a device in which they experience such an acceleration as a centripetal acceleration. So this is going to be AC equals 3g. Specifically, the astronaut is fastened securely at the end of a mechanical arm that then turns at constant speed in a horizontal circle. Let's look at the magnitude. Determine the rotation rate in revolutions per second required to give an astronaut a centripetal acceleration of 3g while in circular motion with radius 9.45 meters. So again, as spoken earlier in class, rotation rate. So we're basically going to get the velocity. We're going to convert the velocity from meters per second to revolutions per second. So first thing we want to get is the velocity, and then use the fact that one revolution is basically one turn around the circle, which is the circumference of the circle, and in order to calculate the velocity in revolutions per second. So centripetal acceleration, AC V squared over R. We need to find out the velocity there. So velocity squared is radius times centripetal acceleration. And so my radius is going to be 9.45. And centripetal acceleration is going to be 3 times 9.8, which is roughly 16.7 meters per second. So now to convert that into revolutions per second, we have to get the distance around the circle. This one revolution, so there's a different conversions for revolutions. So one revolution could be 2 pi radians if we were trying to get it in terms of radians per second, which we'll do when we go into angular velocity, angular acceleration, and all the rotational kinematics. So one revolution is 2 pi radians, 360 degrees. Also, one revolution is just the distance around the circle, which is circumference, which is 2 pi times r. And so once we get that, it should be pretty easy to get revolutions per second. So this revolution of this circle, 2 pi times the radius, 9.45. And that comes out to be roughly 59.4 meters, depending on your stick figs there. So velocity and revolutions per second, we're going to take 16.7 meters per second. And we know that one revolution in this case is equal to 59.4 meters. And that comes out to, gives us our units of revolutions per second. That comes out to be 0.281 revolutions per second. So Emmanuel, at this point, you asked the question, is this the revolution per second? Now that I thought about it again, I wasn't quite sure what your question was, but this is basically, obviously, in 1 second we can get this number of revolutions. And then if we want to figure out how much time it takes to go one full revolution, we can just manipulate this conversion around and do that. So yeah, we can just take this idea, how many revolutions, so 0.281 revolutions per second, and how much time for one revolution. So it's best to just, reciprocate this. So 1 second, 0.281 revolutions, and then number of seconds for one full revolution. And so we're looking at one equals 0.281x. This is basically going to be the unknown x there. And then we just solve for x. Okay. And thus we have 3.6 seconds for 1 revolution. And I think that's what you were asking, just, sorry, I was out of it earlier. Yeah, not sick or anything. I don't, just a little fatigued, but I think I'm getting better. But anyway, yeah, about 4 seconds for 1 revolution. Okay. So let's continue on. So wrap things up here. So now we're talking about the period of time for 1 revolution. We know back to basic kinematics, time is delta x over v. And so we denote period by capital T, it's a type of time period. It's going to not be delta x, which is a linear motion, but around a circle, it's going to be the circumference 2 pi r over v. So if you ever ask the problem, oh, what's the period of rotation? 2 pi r over v. And then you can solve for velocity in this term. Velocity just be 2 pi r over t, which is basically distance over time, the distance around a circle. A little bit on section 4.5. Okay, that's a tangential and radial acceleration. All right, so in section 4.4, we were just keeping the velocity constant on the outside of the circle, but there could be a point where we can have an outside force on the outside of the circle to change the velocity. And now we have a situation that looks like this. As a particle goes around a circle, we have a velocity that looks like this, and then it gets incrementally larger and larger as through time, as this outside force that works linearly is changing the linear tangential velocity through time. So we have tangential acceleration here because the tangential velocity is changing over time, and it's going in a circle too, so the direction is changing. Therefore, we have a radial or centripetal acceleration at the same time. So the total acceleration would just be the Pythagorean sum, or the magnitude of the total acceleration would be the, I'm going to call it A to denote from all T's here. So A is just going to be the total acceleration, which is going to be the sum of the tangential acceleration and the radial acceleration. If you want to find the magnitude of this total acceleration, it's just going to be a Pythagorean sum, AT squared plus AR squared, as we showed earlier in class. And so yeah, I will go over that one example for the total acceleration again. So, and that will end it for this version of today's lesson. Okay, so a car exhibits a constant acceleration of 0.3 meters per second squared, parallel to the roadway. The car passes over a rise in the roadway, such that the top of the rise is shaped like a circle of radius 500 meters. At the moment the car is at the top of the rise, its velocity vector is horizontal, has a magnitude of, this radius in here first. So the tangential velocity, horizontal, is going to be 6 meters per second. So we have this situation, and at this moment, we have a tangential velocity of that 6 meters per second. The radius, however big this guy is, or to draw that whole picture. So, but the radius is 500, and the linear acceleration is 0.3 meters per second squared. So the velocity on the outside is changing, but at this moment it's going to be 6 under the influence of a linear acceleration of 0.3 meters per second squared, covering a hill or a rise with a radius of 500 meters, circular part of the drive there. So then it says, what are the magnitude and direction of the total acceleration vector for the car at this instant? So we're looking for total guy, and saying that A capital T, just leave it alone there, but this is going to be total acceleration. And we need to find that by using the Pythagorean thumb there. So we have the total, or the tangential acceleration. Let's put A sub t here. We have the tangential acceleration. We need to find the radial acceleration. So if the tangential acceleration vector is pointed like this, the radial acceleration will be pointing towards the center of the circle. And in relation to our xy plane, we know that that's going to be the negative direction. All of the vectors pointing downwards, so that's going to be negative A sub r, as this is A sub t. And the total the total acceleration vector will look like that, and we just call that A. For lack of confusion with the A capital T, A little t, just keep it as that. So that's an easy find. So A is going to be equal to the tangential acceleration 0.3 squared, and let's find this little guy, this A sub r, and that's going to be negative b squared over r. That's going to be negative 6 over 500. Comes out to be negative 0.072 meters per second squared. And so, we put that value back in here, and that's going to be 0.072. Doesn't matter because it's squared anyway. And then what we'll find is that the total acceleration, as you can see there in your example, is 0.309 meters per second squared. That's the magnitude of the total acceleration. Now let's find the angle at which it's projected, the direction. And we know that, we call it theta, phi, whatever. Tangent theta will just be the the opposite leg, which is negative AR over AT, opposite over adjacent. And to find the angle, inverse tangent negative A sub r over A sub t. And that gives, okay, so negative 0.072 divided by 0.3. As we saw earlier, it's negative 13.5. If you wanted to convert that to radians, you I guess, but that's basically it. And so that's just, I just wanted to do that yet again. Yeah, so I'm just gonna get some rest again. So, but I did want to kind of show you a couple more nuances to this guy. And we'll do more, and we're going to go back to section 6.1 on Wednesday, and let's see if we can, with time permitting, probably not because it's the minimum day, we'll see if we can introduce gravitation, because gravitation is just going to be an application of the centripetal motion. So now we're not just going to be talking about some arbitrary acceleration. We're going to be talking about the acceleration due to the force of gravity between Earth and Moon, Sun and Earth, or any rotating objects around a central force, or under the application of a central force. So that's it for now. Talk to you later.